There we go.
All right, let me start over. We are starting chapter 19, titled The History of Life. Okay, obviously, since this is biology class, we're talking about life. We probably should rewind and figure out, how, when, evidence that it all began. All right, and actually the good news is a lot of this covers information we talked about last year. Let me name some words. Radiometric dating, half-life, fossils. Covered a little bit. Those are the kind of the key terms in this this chapter. We'll first start off talking about fossils. We'll talk about the couple ways fossils are dated. In other words, one's called relative dating, one's called one's called radiometric dating, and one's called relative dating. We'll go into those differences, and then we'll talk a little bit about the time eras, the time frames of Earth's history. One of the projects I have my 8th graders do, I don't think anybody in here, I don't have that 8th grader, but if I did, this is one of the things that I have you do. I have every one of my 8th graders get out a long sheet of paper here, it's like ticker tape. And this is representing all of Earth's history. Okay, so then my first question to the other classes is Earth's history. Okay, well, where did Earth even come from? Okay, now this is not biology. This is like Earth science, like stars, galaxies. So where did Earth come from? A lot of people don't even know that. Okay.
Big planet that exploded.
No, and that's not even, and that's a common answer. I don't know if Justin, you guys heard Justin, he said the Big Bang Theory. That's totally separate from that. Okay? So let's kind of focus, kind of generalize. The Big Bang Theory, besides being a great show on TV, is actually a theory of where the universe, how the universe came to be. I mean, that's not even Earth. That's like the whole shebang. That's like way before Earth. That date is about 16 billion years ago. Okay, 16 billion years ago, predicted date of the universe. Okay, fast forward, fast forward, fast forward. Let's talk about how Earth came to be. You guys remember from 8th grade how solar systems form. A solar system consists of like a sun, maybe two, and then the planets that go around us. Okay, we have a certain solar system, we have a sun, and we have about 8 planets that go around us. That's our solar system. That forms from, it starts off being something called a nebula, if you've ever heard that word. Nebula is just like this big, giant area of gases and dust. They come in really cool shapes, and you probably saw some of them in 8th grade. They were just like these pillars, and one looks, it's just weird arrangements out in outer space of dust and gas. Because of gravity, those big nebulas, the dust and gas, start kind of coming together. And when they come together, they naturally do that because of gravity. And then another natural thing that happens is it starts to spin. So you get this pulling in and this spinning. And then they always compare it to an ice skater who pulls their arms in and starts going really fast. That's what happened in our solar system. So what happened is you had this nebula of dust and gas started coming together and spinning. And at the very center of that, well, it's not really a nebula anymore, but at the very center of that gets really hot. Like really hot. That's where the sun is. Okay? It gets really hot. It gets so hot that something called fusion starts. Fusion, if you guys remember that from last year, you had atoms just slamming into each other. Well, hot. It releases a lot of radiation. That's how the sun powers itself, fusion. There's nothing burning like wood burning. It's different. So you have fusion going there. Now, there's a lot of leftover garbage that didn't get sucked into the sun. Those leftover pieces, parts, all come together and form the different planets. And all solar systems have a different number of planets. We happen to have 8. Other solar systems have more, others have less, whatever. Okay, that is when Earth, that's how Earth formed. Okay, so that date, that's not 16 billion years, that's not the start of the universe. That is way down here at 4.6 billion years ago. So basically that was the birthday of Earth, 4.6 billion years ago. I'll be honest though, you wouldn't want to have been on Earth back then. because even though it's not as hot as the sun was in the middle, it's still really hot. There was no water, there was no land. If you would go and travel there, it would have been a giant ball of fire, basically, just because it was so hot. Took a while to cool down. In fact, we're talking millions, if not billions of years. And then at about 3.5 billion years ago, bam, is when they thought life originated. 4.6 billion Earth formed, came of all. 3.5 billion years ago, first life. So that's what we're concerned about in this chapter. You know, if this was an earth science class, you'd go into the formation of the earth, formation of the universe. But we're not doing that. We're interested in life, being biology class. So this chapter is all about that. So I want you to know that date. I want you to know that 3.5 billion with a B years ago is when the first form of life is believed to have come into existence. And we'll talk about some experiments that were done to come up with that number. And we'll talk even briefly later in the chapter about where they think or how they think that even came to be. Okay, but before we do that, let's talk about fossils real quick. Remember, fossils are the remains of any organisms. That's pretty straightforward. Hey, it's not easy to form a fossil. People think that if an organism dies, all of them turn into fossils. Mm-mm. In order for fossils to form, they must bury themselves quickly. In other words, if a fossil is going to have any chance of forming out of an organism, that organism better die and it better be covered up real quick. Well, makes sense though, because otherwise little scavenger animals are going to come around and take off a leg and take off this and take off that and spread it all over the place and you got nothing left. So the best fossils, the ones that kind of especially show like the whole organism intact, have to be buried quickly. Most fossils that have ever originate in ocean or lake floors. Most of the fossils that have ever, most of the good fossils that have ever been discovered were basically formed on the bottom of an ocean or the bottom of a lake or something like that. Because there you kind of have a really good chance of it being untouched for a while. And that's what you need for a fossil to kind of be, to be born or to form. Fossils only form, for the most part, in sedimentary rock. Ooh, that's kind of another little side note. I'm writing down 3 words here. Sedimentary, igneous, and metamorphic. This is information you need to know for the OGT. Sedimentary, igneous, and metamorphic. Those are 3 types of rock. The 3 major types of rock that I want you to be familiar with. Now, for our discussion here with fossils, the reason I brought this up is because fossils are really only going to form in sedimentary rock. But the other 2 exist. Igneous rock, where's that come from? Anybody know?
Volcanoes.
That's right. I want you to associate the word volcano with igneous. You can even write that word down next to it. In other words, when volcanoes shoot out their lava, that lava will flow, it'll eventually cool, and it'll form into rock. I don't know if you guys realize this, but volcanoes are the reason we have new land. Okay, they're bringing up the new rock in a liquid form, and then it solidifies and becomes rock. That rock that's just formed from volcanoes is called igneous rock. Okay, sedimentary rock, we'll go backwards. Sedimentary rock, as the word describes, sediments. Sedimentary rock is the rock that is formed from sediments accumulating over time. Usually something erodes in one area and it accumulates in another area, and it builds and builds and it builds and it builds and it builds. That's sedimentary rock. That's why it's so great for fossils, because fossils get trapped in its layers. Okay, metamorphic rock, morphic changing. The word morph is changing. Either sedimentary rock or igneous rock has the ability to become metamorphic rock. All that means is it's rock that was originally one of these two, but because of heat and pressure and time, it changes the composition of a rock a little bit. So metamorphic rock is just a fancy way of saying it's a rock that was once something else and now it's something different because of heat and pressure. Like I said, back in 7th grade, I think, you guys really went into the different kinds of rocks and minerals and all that. We won't do that here, but I did want to remind you about the 3 major types of rock because that's important to know. Okay. Another thing, the remains are replaced with rock. If you are lucky enough to get your hands on a fossil, your chances are, not always, but chances are you're not actually holding the actual skin or organs or bone of that organism. That's long since gone. What fossils usually are, what happens is this: an organism dies, gets buried, all those parts, like organs and skin and everything else, are going to decay. You know, there's bacteria living in there. But they're going to decay slowly if they're buried just right. There's a lot of water, groundwater. Groundwater contains a lot of minerals, like calcium and everything else. Those minerals and that groundwater is going to seep into where the organism is. All those pieces, parts of the organism's going to get replaced with the minerals and the groundwater. So really, fossils, for the most part, if you see one, are actually rock. Like, you're physically holding rock. Now, it's in the same shape and form as your organism, but it's technically rock. I know I'm not going to pass these around today, but like, you know, a good example. You know, this is a fossil here. It's a real fossil. But it's rock. It is technically a rock, but this was once an organism. The organism has kind of dissolved and decayed away, but it was replaced with rock in the same form that it existed when it was alive. So it's actually kind of neat. I don't know what this thing is. I'm not sure, but... so that's kind of that. Has anybody ever been... If you've ever been out to Arizona, and I've never have been, but you see it in the cartoons sometimes, a petrified forest. Have you ever heard of the petrified forest? It's actually a forest of trees that were around a long time ago. And the trees have died, you know, obviously a long time ago, but they somehow got buried real quickly. Remember, plants can make fossils too. They got buried really quickly, and then over time, the wood that made up the trees was replaced with stone. And so if you go to this petrified forest in Arizona, you're basically looking at these stone remains of trees, these trees that are actually stone. That's why they call it petrified forest. So, kind of cool. So that's kind of that. Another thing I want you to remember, something called the law of superposition. It's a law in science. Youngest rock layers are on top. Oldest rock layers on the bottom. If I ever went digging in the dirt, I go out west of Colorado, there's lots of fossils. Sedimentary rock lays down in layers. That's what I have up here. I have a bunch of layers represented by lines. In those layers of rocks are certain organisms that I'm going to represent by symbols, just because I can't draw little organisms. Okay, so I have 4 different organisms, each in a different layer. You should be able to tell me that the organism represented by the star is the youngest of the fossils seen in this picture. Why? Merely because it's located on the layer closest to the surface. It's on the top.
What layer is that?
Hmm?
What layer is that?
What do you mean? What layer is it? It doesn't matter. It's all just. You know, I would just say I would call this just the surface. I would call this as you go, you know, into the earth more. All you need to know is kind of the layers closer to the surface are the ones that are younger. This is almost like a timeline. So you can look at this, a picture like this, and tell me, well, the star, organism, that whatever is representing the star, is the youngest of these. In other words, it lived most recent in time. The circle is a little older than that one. The triangle is a little older than the circle, and the little cubey thing is a little older than a triangle. This gives you just a general idea of how old things are. There's no dates. I have no numbers here. I don't know the numbers at all. But it's giving you just a basic general idea of which ones are older and which ones are newer. This is given a term called relative dating. No, not dating somebody in your family. Relative dating. You can't, exactly, that's called something different. Relative dating is you're basically giving a relative amount of information. It's, in other words, you're giving a general idea of which fossils are older and which fossils are newer. There's no dates, there's no math, there's no nothing, no numbers, no nothing like that. But you're giving a general idea of who's older and who's younger. This is really important. You see this on an OGT test quite a lot. This is the analogy I use to remember which one's younger and which one's older. Let's say you guys, well, you guys are hunters, a lot of hunters in here. I'll use you guys as an example. Let's say you have a subscription to like a hunting magazine, okay, and you get a magazine in the mail every month. Okay, it's January, so you go home today, and in the mail comes this magazine. Okay, you read it like you would, and then you plop it on a table off to the side. Okay. Then February rolls around. You get another magazine in the mail. You read that. You plop it on the table on top of the other one. March comes along. Read that magazine. You plop it on top of February. You get the idea. April, May, June. You got a stack of newspaper or a stack of magazines now. The youngest one, the one you received most recently, is on the top. The one you received way back in January is all the way on the bottom. Remember that when you're talking about fossils and layers and which ones are older and which ones are newer. I'll give you a good idea. Like I said, you see that question pop up on an OGT quite often. Okay. One other word that goes along with this. Actually, I'll just kind of give you the notes. These are pretty straightforward. I'll let you copy. An index fossil. Index fossils are cool. Not every fossil is an index fossil. Yeah, it looks like one. I brought up some pictures here for you guys to see. Trilobites are awesome critters, and I want you to associate the word trilobite with an index fossil. Trilobites aren't around anymore. They're extinct, unfortunately, because they're cool critters. But a trilobite is an example of an index fossil. Why? Because certain fossils can be used like an index, like a guide. You know how your index in the back of a textbook is like a guide to what's in that book? Well, index fossils work the same way. They're kind of like a guide. So you can take an index fossil and compare it to another fossil and get your answer. Must occur in only a few layers, i.e., in other words, only existed for a short time in history. That's one characteristic an index fossil must have. Another one, must be easy to recognize. I drew a really bad picture of a trilobite over here because they're like segmented and really cool. I'll show you some real pictures of them in a minute.
You should have a fossil.
Did you have a trilobite? Who said that? Oh, cool. Yeah, they're pretty common. They're pretty awesome. They actually, and yeah, the people I've been known, some of my students have said they even dug one up around here. Very cool. Must be widely distributed. What that means is, in order for something to be considered a good index fossil, it better be lots of places around Earth. It does no good, you'll see, to have an index fossil that is just found in a small group of islands off the coast of South America, because unless you're digging on those tiny islands off the coast of South America, it's going to do you no good. Okay, here's what an index fossil does. Let's say I decide to go out west to do a fossil dig. I'm going to Colorado. There's a lot of fossils over there. Okay, I'm going to Colorado for a fossil dig, and I got my hat on, I got my clothes on, I'm my cool, awesome fossil paleontologist clothes, and I'm digging in the layers. And I find myself a trilobite. Cool, a trilobite. They're easy to recognize. Here, let me show you what they look like. So I'm going to find myself a trilobite. And like I said, when you see these pictures here in a second, once you see them, you'll never forget what they look like, because they're cool critters.
Horseshoe crabs.
Mm-hmm. Yeah, they do look like horseshoe crabs. In fact, wouldn't be surprised if that's been kind of a offspring of them. Okay. Your classic trilobite kind of looks like that. Okay, obviously this is a fossil. These things aren't around anymore. Okay, it's a fossil one. Segmented. This is what I mean. They have all these segments that kind of run the body. So I'm digging out in Colorado. I've got myself I found myself a trilobite. And I'm like, cool, I got myself a trilobite. And they come in different shapes. They actually kind of look pretty freaky at times.
Is that real?
I don't know. It's a good question. I don't know if it's just a cast or an actual one. But you can see they kind of have the same basic shape. So that's what I mean by one of the characteristics of an index fossil, as you just wrote down, has to be easy to recognize. They're easy to recognize. Okay, so then I'm digging, and then I got myself a trilobite, and then I do a little more digging, and I find this other fossil, and I bring it out, and I'm like, cool, I don't know what this is. Okay, let's say I discover this unknown fossil. It's not a trilobite, it's something else. Now, I give it to my friend, hey, what is this? Well, I've never seen it before. Maybe it's something new, never been discovered. You may not know what that organism is, but because that organism was located near a trilobite, you know the time frame that it existed. Trilobites only appeared a short period of time in Earth's history. It was only pretty much during the dinosaur era. Very short time. So I know my unknown fossil that I just found, I'm pretty darn sure that thing existed during the dinosaurs as well. I still don't know where it is, or I still don't know what it is, but I know at least a time frame of when it existed. That's relative dating. That's dating using index fossils and other fossils as kind of like a guide. So that's kind of like I said, that's one characteristic. Yeah, no, that's it. Let me show you some other pictures and I'll kind of move on. So that's kind of what an index fossil is. They come in some freaky shapes. Yeah, they did. They actually had swimming versions of themselves. Some lived on land, some lived in the water. They came big, they came small. Another cool thing that scientists have noticed about these little suckers is their shape seems to match up with the kind of environment they were in. So within the dinosaur era, there were really calm times and really not so calm times. There were really hostile, a lot of predators around. Trilobites like this that seem to have spikes and armor and all these other adaptations have been known to be found in times where they know there were like a lot of predators or a really strange environment. So it's pretty cool about these things.
What makes them have 3 in their name?
Like trilo, I don't
Yeah.
know. That's a good question. I honestly don't know. I wonder if it's tri or trilo means something. I gotta look that up. That's a really good question. Does Kirsten asked, I wonder where tri and trilobites comes from. I honestly do not know the answer to that question. I don't know if tri,
Where does bites come from?
trilobite. I don't know. I don't know where the word trilobite comes from.
Maybe there's sort of 3 body parts.
That was the first thing that came to mind, and that could be it.
Second part and legs.
Yeah, and that makes sense. And I honestly don't know.
Can you put it back on your flash thingy
On the what?
overhead? I
Yeah.
didn't give it.
Oh, okay. Yep. Okay. All right, so index fossils. Trilobites are great index fossils, and I know there's other examples of other organisms that are used as index fossils, but trilobites are the classic textbook example. Yeah, trilobites are kind of nice. They're found everywhere on Earth, so you can go dig in your own yard. You can actually dig out west. You can dig on the other side of the globe, and you'll find a trilobite, and that's good. So if I decide to go for a dig in many places on Earth, I'll know that if I find a trilobite and I find an unknown organism, I'll know a little bit about that. Okay. A simple little activity. Ooh, let's see if we can get started on this, so we can at least get some of it done. Hey, one person from each table, grab